last time what I did was I tried to spend a lot of time on motivating why the SVD is a good thing, right? And hopefully you walked away from that saying to yourself, well, I wish I'd seen this before. It might be useful. Today what we're going to do is all of the theory behind it. The singular value decomposition. Okay, here we go. What's the price that we're after? We're after finding a decomposition of A as U sigma V Hermitian transpose. And again, if you really are kind of fuzzy about this whole complex valued stuff, anytime you see an H, think of transpose, and anytime I do it for complex valued, just think real, and you'll be able to follow along a little bit more easily. Okay? So here we go. That's the price we're after. And what do we have here? A is in C m by n, so it's a rectangular matrix. U is a square matrix. V is a square matrix. And sigma is a rectangular matrix. Otherwise things don't multiply together very well. And sigma has the additional constraint that it's diagonal. Well, it's sort of kind of diagonal, right? It'll have a diagonal component, and then the rest of it is zeros. And then on top of that, all of these entries are real valued, and they are ordered from largest to smallest. Okay, and these here are called the singular values. And then the other thing is that U and V are unitary. Which means that U, Hermitian U, is the identity, which is also equal to U Hermitian, because it's a square matrix, and V, is the identity, which is that. Okay? That's a lot of stuff. Okay? And yes, this is just one of those things that you're going to have to imprint in your brain. Let's prove this. Okay. And we'll see how energetic I am in proving this, how far we actually get. What I'm going to prove first is I'm going to prove that A is equal to U D V Hermitian, where D has that structure. And why do I use D there? Well, initially I don't want to worry about the fact of all of the entries on the diagonal being ordered from largest to smallest. I'm just going to worry about being able to get something of that structure without necessarily having everything in the correct order. What we're going to see is that as we do this, we will accidentally have everything in the proper order anyway, which is convenient, but that's just a little detail we're not going to worry about. So, we're going to make this a diagonal matrix, and we'll pick the symbol delta for the diagonal entries. Okay, this is a heavy-duty proof. And what I did in the notes is I went ahead and wrote this completely as a proof by induction, as one ought to. And therefore, what I'm going to do in class is sort of give the argument that leads one to the insights that then says, oh, clearly this should be done by induction, and at that point you would take out a fresh sheet of paper and you would rewrite all of your insights in a way that would be proved by induction. Okay, so I'm going to give a little bit more the reasoning behind how you get to where you get, as opposed to the clean proof that, say, a mathematician would want to give, because that's what we mathematicians do. We like to give nice, clean, crisp proofs. So let's motivate this. What did we see in class last time? We saw in class last time that if you looked at how the unit ball was transformed, it was transformed into something that was sort of like an ellipse. Yes?
When you say ellipse, are you saying it looks like an ellipse or it is an ellipse?
I think in my notes I specifically have quotes around ellipse.
Okay.
Because it looks like an ellipse. It might be an ellipse. I don't care if it's an ellipse. I just care that it looks like an ellipse.
Okay.
Okay? Good question. So, and what we... Now, this here, in this case, is R2, but of course in general would be Rn, and this here is R2, in general would be Rn. And the important thing is that there is some vector V0 here that gets transformed. Maybe I shouldn't have taken it in that direction, just because I don't want this here to be in the same direction. Let's draw this way. And that particular vector gets transformed into this vector right here. Okay? And visually, what is the property of this vector right here? This is the vector that gets maximally stretched when you apply A to the vector. Okay? Now, how does that transform into something that we saw when we discussed norms? Well, we saw that the 2 norm of A was defined as the maximum over all vectors of length 1 of A times X. Okay? So what we really are saying here is we're going to pick our V0 such that it maximally stretches. It's the vector that it's maximally stretched. Okay? And because it says maximum here, we know that the vector exists. In particular, notice that V0 then has length 1. Okay. And it turns out that that's also sigma 0. This is a scalar. And we're going to give it a label, and we're going to call it sigma 0. Oh, wait a second. At the moment, we're only interested in delta 0. I'm getting ahead of myself. All right? Now, what we're going to do is we're going to say we want a V, and we're going to pick that V to have as its first column V0. Okay? And then we're going to say, okay, this here is a vector in this direction. Obviously, there's also a unit ball that sits right here. Okay. We can take the vector that points in the same direction but has length only 1. And we're going to call that U0. Oops. Well, I don't have I guess I'm going to have to do everything in blue because, oh, there's a black here. Let's see if it works better. Ah, much better. You got it? And we're going to take that and we're going to make that the first column in U. Now, how is U0 related to a V0? Well, U0 is simply A times V0 that has been normalized to be of length. Did I do something wrong? Okay. It's been normalized to be of length 1. But this here we called delta 0. So this is just A times V0 divided by delta 0. Okay. And by the way, all along here, we're assuming that A times V0 is not 0, but notice that the only case under which that could be 0 is if A were the 0 matrix. So we'll have to deal with the case where it's, so essentially we're going to have to say, without loss of generality, let's assume that A is not the 0 matrix. Fair enough? Okay, so now we have all the pieces in place. Okay. Now, what's the next thing? Well, we now have one vector of length 1. What we really would like is a matrix that's unitary, which really means that we want a matrix that has columns that are mutually orthonormal. And we're going to have a really rough time picking exactly this V that we want and this U that we want by picking all of our columns here very cleverly from the beginning. So for the moment, we're going to not look directly for the correct U and V. For the moment, we're simply going to say, we know that there are, let's see, this is 1 column, so this is n minus 1 columns. We know that there are n minus 1 columns that we can fill out the unitary matrix with that are mutually orthonormal. Why? Because there will always be a basis with n vectors in it that's mutually orthonormal if we start with one vector that we know. We can just keep adding vectors until we get a basis. And similarly here, we can come up with a U1 that fills in the rest of it. You with me? Okay. Well, let's see what happens if we play with this U and this V. And to do that, let's make another observation. If A is equal to U times D times V Hermitian transpose, then you can multiply both sides by the Hermitian transpose of U. That wipes this out. And then we can multiply both sides on the right by V. That wipes that out. And we get this right here. So it would be interesting to see what we get if we take these matrices that we defined in this way, and we hit A with U on the left and with V on the right, and let's examine what the structure is of the matrix that comes out of that. If the matrix that comes out of that is magically diagonal, we're done, obviously. We're going to see that we're not quite that lucky, but we'll get partially there. Okay? Let's have a look. U Hermitian A times V is U1 V1 Hermitian A times, oops, should be U. V0 V1. And that can be written as U1 as a row vector, 0, 0. Gosh, see, I claim I can count to 2. In practice, I don't seem to even be able to do that anymore. U1 Hermitian times A times V0 V1. Oops, did I? Yep, I'm doing it right. And if you multiply that out, you get U0 Hermitian V U1 Hermitian times A times V0 A times V1. Okay, this just says, look, if you do A times a matrix that's been partitioned by columns, it's same as A times first part, A times the second part. Okay, and if you multiply this out, there's a pattern here that you sort of may want to register in your brain. Whenever I try to multiply this out, I say, well, if these were actual numbers, what is it that I would do? Well, it would be the matrix that's 1 times 3, 1 times 4, 2 times 3, 2 times 4. Well, if I'm faced here with exactly the same thing except with symbols, you simply execute exactly the same algorithm, except you have to be careful that you don't commute, because matrix multiplication doesn't commute, or not necessarily, right? So this is just U0 Hermitian A times V0 U0 U1 Hermitian A times V0 U0 Hermitian A times V1 and U1 Hermitian A times V1. Okay? Now, notice that this is this, which is then just delta times U0. Right? Which means that delta 0 times U0. Means that this is just delta 0 times U0. But notice that delta 0 times U0, U0 Hermitian delta 0 times U0 is the same as bringing the scalar up front. But we picked this vector to be of length 1, so that's just delta 0. So the good news is that in our matrix, we at least have a scalar in the right place. Okay? Now this right here, U1 Hermitian times A times V0 is U1 Hermitian delta 0 times U0. Again, a scalar you can always bring out front. So that's delta 0 times U1 Hermitian U0. But what do we know about the columns in U1 versus the column U0? Or orthonormal. And therefore this is just the 0 vector. And therefore this is just the 0 vector. So this here is a column of zeros. Ah, so far so good, right? Unfortunately, there isn't a whole lot that we can say about this. About the only thing we can do at the moment is we can say, well, we can give it a label. We'll say that W is equal to, well, we'll just say that W Hermitian transpose is equal to this right here. So we'll give it a name. It's some kind of row vector, but we don't know exactly what it is. And for the moment, we can't really be so lucky as to have picked our U1 and V1 in such a way that it's diagonal. We don't know yet even if we can do that. And therefore, all we can do is give that a name, and we call it B. Fair enough? Now, we would have been a lot happier if this was 0, right? Because then you might have been able to say,
And then you continue with B by doing the same thing over and over again. And then maybe somehow magically we would have ended up with a diagonal matrix, or eventually B would have become a zero matrix, in which case we're done. Okay? So, we need to convince ourselves that actually W is the zero vector. Okay? That's the next thing we must do. And that gets a little bit tricky. Tricky enough that I'm going to have to consult my notes to make sure I don't mess up. Okay? Now, what is the key? The key is going to be to make the argument that if W is not 0, then we can construct a vector that's not V0 such that this here is actually greater than that. Yes?
I'm sorry, this is going back just a little bit.
All right.
Can we do the U times V times A times V equality right there?
This here?
Up one, sorry.
Up one, here.
Right there. How do you get from that step to the next one where you slice?
The opposite direction?
Yeah.
From here to here? Okay, we can explain that.
So that U naught is a rail.
Okay, this is the way to think about it. We have a matrix that consists of columns where we've labeled this U0 and we've labeled this big U1, right? We now want to take, forget about the Hermitian transpose. Let's take the transpose of that. That's a little easier, right? When you do a transpose, everything that was a column becomes a row. So this becomes that, but we should label that as U0 transpose because it's the vector turned on the side. And if we then have a Hermitian transpose, we should make this a Hermitian transpose. And then this entire matrix, what you're really saying is that matrix needs to also be turned on its side. So that becomes U1 Hermitian transpose.
Okay, so you're labeling it. Okay, you're not saying take. Okay.
Got it? If you have trouble with this business of looking at blocked matrices and doing operations with them, in these notes, these undergraduate notes of mine, I go in great detail about that. So, those of you who don't see these kinds of things, ask questions. I'm always willing to stop in the middle of class and or go back to the notes. All right, good question. Everybody else had that same question and was afraid to answer. So let's go back. The argument we're going to make is that we can, if this is not 0, then we can construct an x that has the property that the 2 norm of A times that x is greater than this, which then violates our assumption that V0 was the vector that maximized this. Okay? So, let's erase all of this because we're going to need some room. And we're going to look at delta 0. Remember, it's a real number because it was the 2 norm of the matrix. It's always convenient to square it when we reason about this, because inherently, when 2 norms come up, working with the square avoids that square root. We know that that's equal to A times the 2 norm of that. Okay. Now, we saw had you done the early exercises in this section, or in these notes for today and tomorrow, and that are due on Tuesday, then you would have proven to yourself that if you have unitary matrices U and V, then U times U Hermitian times A times V in 2 norm is the same as that. Okay. And why is that? Well, we argued that working with U and V and left and right really was a matter of changing the orthogonal basis in which you express your vectors. If you don't, if it's a unitary, if it's an orthonormal basis, then that doesn't change the length of the vector, and therefore the two norms should be preserved along the way. Okay? That's the general idea there. So we have this. And we just discovered that if you compute this, that's this, which was equal to that, was equal to that, etc. So we get this right here. Fair enough? Okay. Now, we know that that's equal to, by definition, the max of over all vectors x that are not a zero vector of delta W0b times vector x squared over x squared. Okay? And here I'm just carrying the squares through. Okay, so there is some vector that maximizes this. Okay. Here's a trick that we use over and over and over again, and that is, if you're trying to come up with a, which is, if you plug in a specific vector x, then obviously the maximum over all x is going to dominate that. Right? And what is the specific vector x that you want to pick here? Okay. Well, notice that I'm going to have to look at my piece of paper here, which goes to show that this is a well-known trick. Okay? If you don't know the trick, you'd have to play around with it a little bit to come up with what the trick was. Or if you're like me and you forget the trick, you'd have to play around with it for a little while, which I probably could, but I'm not going to. I'm going to cheat. All right? And the reason why I'm pointing this out is that, look, there's no shame in forgetting the trick. What I want you to understand is what the general strategy is, so that you can then think about, what exactly was that vector again, right? And the trick is, well, you can sort of, this should be a delta zero, right? Well, you can sort of see that you may want to come up with something in the end that's greater than delta zero squared. So it'd be nice to get a delta zero squared to somehow pop up. And notice if you multiply this times delta zero for the first entry, then you get this times that, which gives you your delta zero squared. Okay? Also, we would like to argue that this is of length 0, because then it's the zero vector. So it would be nice if somehow a W Hermitian W shows up, because that's the square of the length of the vector W. And if we can prove that that's 0, then we're home free, right? So let's try putting W there.
Is that W or W Hermitian?
That's a W, because this has to be a vector, right?
Okay.
And actually, that's a really good question to always ask yourself. Does the shape of what I'm plugging in here make sense? And that's why we're so careful trying to always take a row vector and put either a transpose or a Hermitian transpose on it, because then immediately you can see, oh, this has the following shape. Does this make sense in this situation? If you then multiply that out, you get that that's equal to the 2 norm of delta 0 squared plus W Hermitian W. 0, it's this times that plus this times that. Notice again that the pattern is, if these were individual elements, then your multiplication would be this times that plus this times that. Just because there are symbols here doesn't change that. Okay, so we get that, and then we get this times that plus this times that, which is B times W. And then on the bottom, this is just d0 squared plus w Hermitian w, because that's what this is, right? The 2 norm of a vector is just x Hermitian x, and if you multiply this out for this vector, it's right here. Do I have everything there? Okay. Now, the cool thing is that anytime you have a vector and you add something to it, you only make its length longer, okay? So in other words, if you take a vector and you set some of its coefficients equal to 0, you make the vector shorter. The point being that this is greater than or equal to the vector that only has delta squared plus w Hermitian w as its first element, and 0 is for the rest, divided by delta 0 squared plus w Hermitian w. Am I doing this right? Okay. And notice that this is just a vector with an individual element, right? So this is just this element squared plus the sum of the rest of the elements squared. And that's just delta 0 squared plus w Hermitian w squared, divided by delta 0 squared plus w Hermitian w. And that, of course, is just
I have a question.
yes.
You seem to be dividing by 0.
Yeah, so this is notation. Remember that when we take a vector that has a whole bunch of entries,
Yes.
and we put this. Yeah, so
Duh.
it divides the vector into the first element and the rest.
Sorry.
Yeah, no, keep asking those questions because I've been doing this so long that it doesn't register in my brain.
Yeah.
Okay, so always ask those questions, please, please, please. Even if you know what I mean, you may say, you may want to point out that, okay? And that's a kind way of telling me, we're not all quite as familiar with the notation yet. Very good, I'm glad you asked. You with me? And what we've just discovered is that delta 0 squared is greater than or equal to this, and from that we can conclude that w must be the 0 vector. All right? So, what we now know is that in fact there's a 0 sitting here. Okay? So what do we have? Just to recap, we have that u0, u1 Hermitian times a times v0 v1 is equal to delta 0 0 0 b, where this is some matrix. Okay? And then what you can say is, well, you can do the same thing with this matrix B. Or you can say, well, if we did a proof by induction, then we might have been able to assume that this has a singular value decomposition, or that this has the kind of decomposition that we're after. And then maybe we can do something with that. Okay? And this is where, in my notes, I've rewritten it as a proof by induction. Because then what I can say is, by the inductive hypothesis, I can replace this by delta 0, 0, 0, 0, and then a b would be sum u sub b times sigma sub b times v sub b Hermitian transpose. Oops. Except we don't know yet that that's a sigma. So this would be a d. Yes?
So if we say that we can do induction on this, aren't we assuming that the u sub v times u naught is orthonormal is a unitary matrix?
Yes.
Shouldn't we have to prove that assumption?
Not if we do it by induction, right? That would be the inductive hypothesis. What we would have to do is prove a base case. Okay? Usually you say, prove it for matrices that are
Yeah,
0 by
I
0.
think that we can't be sure that this would exist in the first place. Right? That this should be a valid operation even if we do a proof by induction. Right?
No, but when you prove a result like this by induction, you usually say, assume it's true for the smaller matrix. Now prove that under the assumption that it's true for the smaller matrix, it's also true for the bigger matrix, right?
Right.
So here I'm sort of saying, had we properly set this up as a proof by induction, then we would have made the inductive hypothesis that that B, some matrix B that's n minus 1 by n minus 1, or n minus 1 by n minus 1, has this decomposition,
All right.
and then you would bootstrap yourself up from that.
Okay. So
Okay.
then we would have to prove that U0 combined with UB will still be an operation.
We're there. Yeah, that's where we need to go next. You're right. Yes?
Okay, I'll go back because I don't get why you changed it to 0, the W.
The W to 0?
Yeah, W.
Well, we argued that delta 0 squared was greater than or equal to delta 0 squared plus W Hermitian W. That forces W to have length 0. The only vector that has length 0 is the 0 vector.
Okay.
And therefore we can go in and plug it in. All right? All the details are actually in the deductive proof, okay? And there you'll be able to go, oh, I can follow along, I can follow along, I can follow along. But then you'll say, but how did he actually have all of these insights so that we got here? So I'm trying to give you the insights that lead you to the insights that allow you to then construct things as in inductive proof. You with me? That's my job today. So now we have this. Of course, this has nothing to do with what's up here. This result here, you can write as delta 0 dB 0, 0 times the matrix 1, 0, 0 UB times the matrix 1, 0, 0 VB permission. That's a matter of recognizing that when you do this block matrix multiply, the first element is this times that plus this times that. The second element is this times that plus this times that. That's just 0. This times that plus this times that is 0. This times that plus this times that is this first part here. And then you multiply from the right, and you get the same thing. And it's not hard to check that if this is unitary, then this matrix is unitary. All right? And then what you can do is say, if we call this U and we call this V, then you can multiply this by U on the left. So what we've now established is this. Actually, let's call this UA and this VA so that we don't get confused. Okay? We can then go and multiply this on the left by U and this on the right by V Hermitian. And if we do that, we need to multiply this by U on this side and this by V Hermitian on this side with subscripts A. Right? And then you can take all of this, and one of the exercises that I want you to do for Tuesday is to show that if you multiply two unitary matrices together, you get another unitary matrix. And therefore, you can call this the unitary matrix U. You can call this the unitary matrix V, which of course then would have a Hermitian on it. And you've got the result that you want. Right? That fills in the last one. Sort of, kind of see it? Right? Okay, so this is where you then have to go and very carefully go through the proof that I have in the notes to recognize how I now rearrange this into the proper proof by induction that gives all of the details. Okay, and I don't think we need to spend our time on that. I mean, do people want me to put it on the screen at least? maybe you should look at it and then you can ask questions about it on Tuesday if you have it. How's that? All right? The question?
You assign UA as U0 and U1. But
Yes.
then on this board you have
Yeah,
U as U0 and U1. So which one is exactly UA?
Well, all I did was I gave this a different name. I can always give multiple names to the same thing, right? The fact is that I should never have called this U on this side, because the U that we were after was the U that satisfied this. And as we were doing this, we discovered that the U that we were constructing didn't quite have this property yet. It only had the property that it took us one step. So then when we got over here, I decided I should have been smart. I should have called it U sub A so I could distinguish it from the actual U that we were after. Okay? Now, you could say Van de Geijn should have done his homework better and therefore given a much cleaner proof. But the fact is that I think it's much better for me to model the thought process that one might go through making small little errors like this along the way to then finally come up with the insights that you can then rewrite as a very clean proof than it is for me to simply present the clean proof, which you can then admire, and you can then say, boy, Van de Geijn must be really smart because he can do these beautiful proofs, but you don't learn much from it, right? That's the point. I want you to learn. I don't want you to sit there and admire. As a matter of fact, if in the end you walk away saying, you know, everything I learned in this class was really trivial, because look how well I now understand it, and therefore Van de Geijn can't be all that smart because I understand it too, that's exactly where I want you to be. All right? Okay? Sometimes they have these courses that seem to be more like, you know, proofs for poets, where we try to teach you just enough so that you understand how smart we are. That's not for me. Yes?
Could you talk about what happened after we proved W is 0?
How we got that, or what we did with that?
What we did after we proved.
Okay. What we did after we did that was we said, oh, we can set this to 0. Okay? And once we set that to 0, we knew that the U0 and the U1 that we constructed had the property such that if you apply it from the left and from the right, like this, you ended up with a matrix that had a 0 there. Okay. And then what we said was, we can then restart with B. We can find its norm. We can use it to similarly create a thing, doing that for every matrix. And then you have to sort of say, and can we then recover from that the actual thing we want? And the recovering coming back out of it was, if we do get a VB and a UB and a VB for that B, then can we come up with what we want for the original A? And that's sort of getting back out of it. Got it? Okay. This is the kind of thing where it actually helps when you do the homework to get together in groups so you can talk about these things so that you don't bang your head against the wall. You should also feel free to post on Piazza and ask others for help. There's no better way to learn the material than helping others, etc., etc. All right? And again, you know, this trick of what to do with the W, you know, it's a trick. And if you've had enough experience, you can see those kinds of tricks. You know, I tend to not hold people responsible for those kinds of tricks. Okay? Which is why ideally in this kind of class we would have an oral exam individually with each of those, because when we would then get to a point like this, I would give you a hint. Try the following vector and see what happens. Okay? And then you would work through it. Unfortunately, doing oral exams with a class of 55 is not entirely practical. Which is why you should get together in small groups and then you can give each other hints. All right? Okay, can we move on? So, what we now have is the result that we want for the singular value decomposition, except with the matrix D, where we have not shown that the elements of D appear in order from largest to smallest as you go along. Okay? And the fact is that you can show that the 2 norm of A is the same as the 2 norm of this. And then you can show that if this is the 2 norm of A, then, sorry, it's the same as the 2 norm of this. And then you can show that if the 2 norm of this is that, then the 2 norm of B must be less than or equal to that. And therefore, it means that every time you go through this recursive step to find yet another U and V, you will always find elements that are always smaller than the one that you found in the first place. And that's why they come out in order. Or you can say, by cleverly swapping columns of U and V, I can always take the diagonal elements that are not in order and put them in order. That's another way you can argue why it's not that important to get them in order. All right? And I think that's a homework exercise, so you can play around with that. Okay, so that's the singular value decomposition. All right? Now, what's next? We've done the theorem. We've done the geometric interpretation already. We did that last time. So let's not go over that again. Let's look at some consequences. Yes?
I have a question. So, considering how we went about doing this proof,
Yes?
it looks as though it's not all that hard to get these delta values or the sigma values from the SVD.
Correct.
Is this how the algorithm for SVD would work?
Well, to get the delta...
Also, the expensive operation is in finding the delta zero or the vector
Okay,
delta.
okay. You think ahead. The last section of the notes is, I'll read it to you, an algorithm for computing the SVD, question mark. So what you're saying here is that it seems like I have described an algorithm, right? What would the algorithm be? I'm very happy that you asked that. So since you asked it now, we'll skip to the last section of the notes, okay? What you're saying is, the key seems to be to find the 2 norm of A, because that gives you delta, and with that find the V0 that maximized, okay? The inconvenient truth is that that's actually hard to find. Okay, so that operation in itself is actually expensive. However, let's say that this was passed down. Obviously, if you're doing this in MATLAB, there's a routine for finding the 2 norm of the matrix. I wonder if there is if that routine can return to you the vector that actually does it. But once you have delta 0, it's not that hard to find V0. Okay, let's just say that. So let's say we get those magically. Then what do we need to do? Well, then finding U0 is easy because it's a matrix vector multiply. That's order n squared computation. And then dividing by delta 0 is g, right? So that's easy. The key then is that you have to find other orthonormal columns, okay? In the next topic of the course, we're going to find that that costs order n cubed computation. Ooh, that's expensive. Okay? So what we would end up with is an algorithm that for every step has order n cubed computation. You would have to do that for n steps. Obviously, at every step, the matrix would shrink, but still, you would end up with an order n to the 4th cost. In my world, order n to the 3rd computation is acceptable. Order n to the 4th is not. Okay, so doing a computation with something that's order n cubed on the largest machine in the world for, say, a million by million matrix takes about 15 minutes or so to finish. But if you multiply that by another million because it's order n to the 4th, okay? Yeah, I mean literally, you'll be dead by the time the answer comes. So, not a good thing. Excellent question. So, we will talk about practical algorithms for approximating the singular value decomposition at the end of the course. We'll get there. And I think that the most practical algorithm for finding all singular values, and well, for finding the complete singular value decomposition of a dense matrix, we actually just published a paper on. So, you know, this is obviously very dear to my heart. And trust me, you'll be able to understand that paper by the time you're done with this class, which again then will make you wonder, how smart can Van de Geijn be anyway, right? And that's a good thing. That's a good thing. All right? So there we are. Consequences of the singular value decomposition.
When you publish these papers, do you use your own notation or do you have to use the rest of the world notation?
We pick and choose. If it's convenient for us to use our notation, we use our notation. If it's convenient for us to use some other notation, we use other notation. Okay? Often, our notation, we believe, is the cleanest way to present. For that particular paper, I think we use more conventional notation. Because you're going to find that inherently for those operations, working with the individual entries actually is what you have to do. Right?
Oh, sorry. I didn't catch the part why U1 Hermitian, U0 is 0.
Ah, good point. We know that U is unitary. Okay? If you partition U by columns like that, what you get is U0 Hermitian, U1 Hermitian times U0, U1. We pulled that trick somewhere else. And if you multiply this out, again, you go back to what if these were just individual entries. This would be an outer product, right? It would be this times that for the first entry, this times that for the second entry, etc. So what you get is U0 Hermitian, U0, U0 Hermitian, U1, U1 Hermitian, U0, U1 Hermitian, U1. But you know that that has to be equal to the identity. And that means that this must be the 0 vector. So that's one way of looking at it. Another way of looking at it is, listen, the columns of this matrix must be mutually orthonormal. That means that this column must be orthonormal to all of the other columns. If you look at what U1 Hermitian U0 does, okay, it does this dot product with that, this dot product with that, but really these are the columns of this matrix, right? Which means that this dot product with that must be 0, because this row is one of the columns of U1. All of the columns of U must be mutually orthonormal. So if you take any one column of U1, it must be orthogonal to this vector that's the first column. Therefore, its dot product must be 0. And that's another way of arguing. Sometimes I say these things a little too fast. Rewinding me is a good thing. All right? Good. Any other detail that needs to be filled in? Notice that in this class, what we essentially did was say, well, you all took a linear algebra course, therefore you must be good at this. So let's jump straight into the hardest subject in linear algebra and present that first. Here's the singular value decomposition, and here's all the complex math you have to understand it. Okay? Therefore, it is good to ask questions. It's okay. All right? You with me? The irony is that the rest of the semester, therefore, is going to look so much simpler. Just survive this part, you're good. Okay. consequences of the singular value decomposition. If we don't get moving here, we're not going to get to that. Or maybe different interpretations. Okay. We have that A is equal to U sigma V Hermitian transpose, right? What do I like to do? I like to partition my matrices by columns. This matrix has m columns. I like to take V, partition it by columns. And then I'm going to have to take this and partition it by. And this is inherently how that matrix looks, right? Now, what happens when you take a matrix that you view as columns and you multiply it on the right by a diagonal matrix? Scale what? Scale columns, right? By the way, if I ever say scale what, you could simply say scale sir. And that goes back to a joke I always tell, but never mind. Let's not get into jokes now. We're running out of time. All right, here we go. The recognition here is that the first column here is this times that plus this times that, etc. But all of those are 0. So the first column is just sigma 0 times u 0. This times the scalar is the same as the scalar times the vector. And then similarly, this times 0 plus that times the second element plus zeros for the rest gives you a sigma 1 times u1 and so forth, right? If there were m minus 1 sigmas, then you would get this. Of course, a bunch of those would be 0. And then you multiply that times, now if these are by columns, transpose them, we get those vectors as rows. Except that we took each row and we took its transpose. In this case, Hermitian transpose. And we get that. Fair enough? Now, how do I think of this? I always go back to having individual entries. 4, 5, 6. I do this times that plus this times that plus this times that. So if I have a bunch of symbols here, it's this times that plus this times that, etc. So what we get is sigma 0 times u0 times v0 Hermitian transpose.
Is this step dimensionally correct because they're becoming the zero sequence?
Because of
These are the m
zeros.
We are multiplying m with.
I think the answer is yes.
So
Okay, I mean, what you're saying is there may be zeros down here as well.
Okay.
Right?
So we're just going to ignore those things when.
Yeah, I mean, well, they multiply the zeros. So they're insignificant, right? Okay. So we would have this all the way up to sigma r minus 1 times v u r minus 1, v r minus 1 Hermitian transpose. And then actually the rest of them would all be 0, right? Okay. Now, what's each of these beasts? Each of these beasts is a scalar times a vector that is being put on its side. Okay? And we have R of those. Each of these is a rank 1 matrix. Okay? So, another interpretation of the singular value decomposition is that any matrix A can be written as a scalar times a rank 1 update, a rank 1 matrix, or a scalar times an outer product, plus a scalar times an outer product, plus a scalar times an outer product, R of those. Okay? And you can sort of see that, what we could then do is, if some of these singular values are very small, we could simply ignore them because they wouldn't be particularly significant, and therefore we can start approximating our matrix with fewer columns of U and fewer columns of V. Another way of expressing that using our blocked notation is to say that A is equal to U times sigma times V Hermitian transpose. You can take your U and partition it into a left part and a right part where these are the first R columns. You can take your matrix sigma and partition it into the block up here that's non-zero and the blocks that are all zero. This makes what you were complaining about completely unambiguous, where the zeros are. And then you take your V and write it as V left, V right, where these are R, and then this is an R by R matrix. If you multiply this out, what do you get? You get this times that plus this times that, so you get a UL times sigma top left plus this times that, which is 0. And then you get this times that plus this times that. That just puts a big fat 0 right there, which you must multiply times VL Hermitian V R Hermitian. That's taking this, taking all the columns, making them into rows, except that we do more than putting it into rows. We actually take the Hermitian transpose. And then if you multiply this times that plus this times that, what you get is UL sigma top left VL Hermitian transpose. Okay. What is that? That is the first R columns here times this block here times the first R columns there, which then if you multiply it out will get you exactly that right here. And that's how the notation relates to that. This is known as the reduced singular value decomposition. Notice that this is typically a rectangular matrix that has orthonormal columns, but is not a unitary matrix because it's no longer square, times a square matrix, times another rectangular matrix put on its side. Okay? Now, you could say, let's take this to be k columns, k by k rows and columns, and k columns where k is less than or equal to r. Then it would be no longer the case. So then you would have had a couple of non-zeros sitting here, and therefore it would no longer be the case, well, this should still be equal, but when you go to this point, it would be only approximate, because now you've taken some stuff that was non-zero and you've pretended for it to be 0. And what you get then is the best rank K matrix approximation. Okay. So in particular, if you have all of these non-zeros and you look at the last ones and you say, boy, those are awfully small, maybe they just came from, error that occurred during the computation or error that occurred when we measured the entries of the data of the matrix. Then you may choose to simply pretend that those are 0, and you would then get the best approximation. And you might even get a better matrix than you started with, because it might be that you threw away noise that somehow crept into your data. And that's how often the singular value decomposition is used to clean up data. Okay? What other things do we have? Gosh, I think we're out of time. So, for the rest, you'll have to read the notes. Okay? And then I'm sure that there'll be questions on Tuesday after you do the homework. And we'll have another lively lecture at that point.